Hey everyone and welcome. I'm Lee, a solutions architect at a major IT corporation in Japan, and I am so excited to kick off this new series with you. For my friends and me, it's about more than just passing the AWS Certified Solutions Architect Associate exam. We're passionate about sharing our knowledge with the entire cloud community, especially with all of you who love to learn. Over the next several videos, we'll be going through 500 real exam questions that reflect exactly what you'll see on the SAA-C03 test. But we're not just going to give you the answers. Each question comes with an in-depth explanation based on our real-world experience, helping you understand the why behind every solution. Whether you're studying for your exam in 2025 or just want to level up your cloud skills, this series is for you. Let's get started with our first video, covering questions 1 through 25. Question 1. A bicycle sharing company is developing a multi-tier architecture to track the location of its bicycles during peak operating hours. The company wants to use these data points in its existing analytics platform. A solutions architect must determine the most viable multi-tier option to support this architecture. The data points must be accessible from the REST API. Which action meets these requirements for storing and retrieving location data? Use Amazon Athena with Amazon S3. B. Use Amazon API Gateway with AWS Lambda. C. Use Amazon QuickSight with Amazon Redshift. D. Use Amazon API Gateway with Amazon Kinesis Data Analytics. Okay, this question is about designing a real-time data ingestion and processing architecture. The key here is to find the right combination of services that can handle a high volume of streaming data, ingest it via a REST API, and prepare it for an analytics platform. This isn't just about storing data, it's about the full flow from the bicycle to the analytics platform. With that in mind, let's look at our options. Options A and C are incorrect because they focus on the analytics and reporting side of the architecture, not the real-time ingestion part. Amazon S3 and Amazon Redshift are excellent for storing and querying large datasets, and Amazon Athena and Amazon QuickSight are perfect for analytics and visualization, but none of these options describe how the raw, real-time location data gets into the system in the first place via an API. Option B is also incorrect. While it uses API Gateway to handle the REST API and Lambda for processing, it's not the most viable solution for a high-volume, streaming data workload like this. A dedicated streaming service is more scalable and cost-effective for constant, real-time data ingestion compared to using a Lambda function for every single data point. This brings us to option D, which is the correct and recommended architecture. It perfectly maps each workload to the best tool for the job. You use Amazon API Gateway to provide a scalable REST API endpoint that the bicycles can send their data to. From there, the data is ingested into an Amazon Kinesis data stream, implied by Kinesis Data Analytics, which is designed for high-volume, real-time data streaming. Amazon Kinesis Data Analytics can then process and analyze this data on the fly before it is stored in a service like S3 or Redshift for the existing analytics platform. Therefore, the correct architecture is D. Use Amazon API Gateway with Amazon Kinesis Data Analytics. Question 2. A solutions architect needs to implement a solution to reduce a company's storage costs. All the company's data is in the Amazon S3 standard storage class. The company must keep all data for at least 25 years. Data from the most recent 2 years must be highly available and immediately retrievable. Which solution will meet these requirements? A. Set up an S3 Lifecycle policy to transition objects to S3 Glacier Deep Archive immediately. B. Set up an S3 Lifecycle policy to transition objects to S3 Glacier Deep Archive after 2 years. C. Use S3 Intelligent Tiering. Activate the archiving option to ensure that data is archived in S3 Glacier Deep Archive. D. Set up an S3 Lifecycle policy to transition objects to S3 One Zone Infrequent Access, S3 One Zone IA, immediately and to S3 Glacier Deep Archive after 2 years. Okay, this question is about optimizing storage costs for a long-term data retention policy using Amazon S3. The key is to match the data's retrieval needs with the correct storage class over time, which often involves using S3 lifecycle policies. With that in mind, let's look at our options. Option A is incorrect. The company requires data from the most recent 2 years to be highly available and immediately retrievable. Transitioning the data to S3 Glacier Deep Archive immediately would violate this requirement, as that storage class is designed for long-term archiving with a retrieval time of up to 12 hours. Option C is incorrect. While S3 intelligent tiering automatically moves data between standard and infrequent access tiers, it doesn't automatically move data to S3 Glacier Deep Archive. You have to explicitly configure the archiving option. More importantly, even with the archiving option activated, intelligent tiering's primary purpose is for data with changing access patterns. A predictable, time-based transition is better handled with a standard S3 Lifecycle policy. Option D is incorrect. This option transitions data to S3 Zone IA immediately, which is a low-cost storage class. However, the requirement states that the data from the most recent 2 years must be highly available. S3 Zone IA stores data in a single availability zone and is not considered highly available. Also, it's not the most cost-effective solution for data that is frequently accessed for the first 2 years. This brings us to option B, which is the correct and recommended solution. Perfectly meets all the requirements. The data stays in the S3 standard storage class for the first 2 years, which provides high availability and immediate retrieval. After that 2-year period, the data is no longer needed for immediate access and can be moved to the most cost-effective long-term archival storage class, S3 Glacier Deep Archive. This transition is managed automatically by an S3 Lifecycle policy. Therefore, the correct solution is B. Set up an S3 Lifecycle policy to transition objects to S3 Glacier Deep Archive after 2 years. Question 3. A company operates a food delivery service. Because of recent growth, the company's order processing system is experiencing scaling problems during peak traffic hours. The current architecture includes Amazon EC2 instances in an auto-scaling group that collect orders from an application. A second group of EC2 instances in an auto-scaling group fulfills the orders. The order collection process occurs quickly, but the order fulfillment process can take longer. Data must not be lost because of a scaling event. A solutions architect must ensure that the order collection process and the order fulfillment process can both scale adequately during peak traffic hours. Which solution will meet these requirements? A. Use Amazon CloudWatch to monitor the CPU utilization metric for each instance in both auto-scaling groups. Configure each auto-scaling group's minimum capacity to meet its peak workload value. B. Use Amazon CloudWatch to monitor the CPU utilization metric for each instance in both auto-scaling groups. Configure a CloudWatch alarm to invoke an Amazon Simple Notification Service, Amazon SNS, topic to create additional auto-scaling groups on demand. C. Provision 2 Amazon Simple Queue Service, Amazon SQS queues. Use one SQS queue for order collection. Use the second SQS queue for order fulfillment. Configure the EC2 instances to poll their respective queues. Scale the auto-scaling groups based on notifications that the queues send. D. Provision 2 Amazon Simple Queue Service, Amazon SQS queues. Use one SQS queue for order collection. Use the second SQS queue for order fulfillment. Configure the EC2 instances to poll their respective queues. Scale the auto-scaling groups based on the number of messages in each queue. Okay, this question is about solving a scaling problem for a multi-stage application that experiences unpredictable traffic spikes. The key is to decouple the fast-running order collection process from the potentially slow-running order fulfillment process to ensure that each can scale independently without data loss. With that in mind, let's look at our options. Option A is incorrect. Setting the minimum capacity to the peak workload value would result in significant over-provisioning and high costs during non-peak hours. While this ensures capacity for peaks, it is not a cost-effective or scalable solution. Option B is incorrect. Using an SNS topic to create additional auto-scaling groups is an overly complex and inefficient solution. Auto-scaling groups are designed to scale their own capacity automatically based on metrics and policies, and there is no need to create new groups on demand. Option C is incorrect. While using Amazon SQS is the right approach for decoupling the processes, scaling based on notifications from the queues is not the correct mechanism. Auto-scaling groups should scale based on a metric, not a notification. A more appropriate metric is the number of messages in the queue, which directly indicates the workload. This brings us to option D, which is the correct and recommended solution. Perfectly addresses all the requirements. By using two separate SQS queues, you effectively decouple the two processes. The order collection instances can quickly write messages to their queue, regardless of how long the fulfillment process takes. The fulfillment instances then poll their separate queue for work. The most critical part of this solution is scaling the auto-scaling groups based on the number of messages in each queue. If the number of messages in the fulfillment queue grows, it indicates a backlog, and the auto-scaling group will add more instances to handle the load. This ensures that each stage scales independently based on its specific workload, preventing data loss and providing adequate capacity. Therefore, the correct solution is D, provision 2 Amazon Simple Queue Service, Amazon SQS queues. Use one SQS queue for order collection. Use the second SQS queue for order fulfillment. Configure the EC2 instances to poll their respective queues. Scale the auto-scaling groups based on the number of messages in each queue. Question 4. A company produces batch data that comes from different databases. The company also produces live stream data from network sensors and application APIs. The company needs to consolidate all the data into one place for business analytics. The company needs to process the incoming data and then stage the data in different Amazon S3 buckets. Teams will later run one-time queries and import the data into a business intelligence tool to show key performance indicators, KPIs. Which combination of steps will meet these requirements with the least operational overhead? Choose 2. Use Amazon Athena for one-time queries. Use Amazon QuickSight to create dashboards for KPIs. B. Use Amazon Kinesis Data Analytics for one-time queries. Use Amazon QuickSight to create dashboards for KPIs. C. Create custom AWS Lambda functions to move the individual records from the databases to an Amazon Redshift cluster. D. Use an AWS Glue extract, transform, and load ETL job to convert the data into JSON format. Load the data into multiple Amazon OpenSearch Service, Amazon Elasticsearch Service clusters. E. Use blueprints in AWS Lake Formation to identify the data that can be ingested into a data lake. Use AWS Glue to crawl the source, extract the data, and load the data into Amazon S3 in Apache Parquet format. Okay, this question is about building a data lake for a company with both batch and streaming data sources. The goal is to consolidate all this data into one place for business analytics with the least amount of operational overhead. The solution must support one-time queries and KPI dashboards. With that in mind, let's look at our options. Since we need to choose 2, one will focus on the data ingestion and processing part, and the other will focus on the analytics and querying part. First, let's address the data ingestion and preparation piece. Option C is incorrect because it suggests using custom Lambda functions to move data. This would require significant custom code development and maintenance, leading to high operational overhead. Option D is incorrect. Converting data to JSON is not the most efficient format for analytics, and loading it into multiple OpenSearch service clusters is not the standard data lake pattern for business analytics. OpenSearch is primarily for search and log analytics, not for running ad hoc queries or BI dashboards on a data lake. This brings us to option E. This option describes the core data lake ingestion process. Using AWS Lake Formation blueprints and AWS Glue is a powerful and serverless way to ingest data from various sources, databases, streaming services, and prepare it for analysis. AWS Glue's ability to crawl sources, extract data, and transform it into an efficient columnar format like Apache Parquet, then load it into S3, is the standard, low-overhead approach for building a data lake. Now, let's address the analytics and querying piece. Option B is incorrect because Kinesis Data Analytics is used for real-time stream processing, not for running one-time queries on a staged data lake. This brings us to option A. Once the data is in the S3 data lake, as described in option E, you need a way to query it and build dashboards. Amazon Athena is a serverless query service that allows you to run standard SQL queries directly on data in S3 without managing any infrastructure, which perfectly meets the one-time queries requirement with very low operational overhead. Amazon QuickSight is a fully managed BI service that integrates seamlessly with Athena and S3, making it the perfect tool to create the dashboards for KPIs. Therefore, the correct combination of steps is A and E. Option E sets up the ingestion pipeline for the data lake with minimal overhead using AWS Glue and Lake Formation, and Option A provides the serverless analytics tools, Athena and QuickSight, to query that data and create dashboards. Question 5. A company performs monthly maintenance on its AWS infrastructure. During these maintenance activities, the company needs to rotate the credentials for its Amazon RDS for MySQL databases across multiple AWS regions. Which solution will meet these requirements with the least operational overhead? A. Store the credentials as secrets in AWS Secrets Manager. Use multi-region secret replication for the required regions. Configure Secrets Manager to rotate the secrets on a schedule. B. Store the credentials as secrets in AWS Systems Manager by creating a secure string parameter. Use multi-region secret replication for the required regions. Configure Systems Manager to rotate the secrets on a schedule. C. Store the credentials in an Amazon S3 bucket that has server-side encryption, SSE, enabled. Use Amazon Event Bridge, Amazon CloudWatch events, to invoke an AWS Lambda function to rotate the credentials. D. Encrypt the credentials as secrets by using AWS Key Management Service, AWS KMS, Multi-Region Customer Managed Keys. Store the secrets in an Amazon DynamoDB global table. Use an AWS Lambda function to retrieve the secrets from DynamoDB. Use the RDS API to rotate the secrets. Okay, this question is about securely managing and automatically rotating database credentials across multiple AWS regions with minimal effort. The key requirements are security, multi-region support, and low operational overhead. With that in mind, let's look at our options. Option B is incorrect. While AWS Systems Manager Parameter Store can store secure strings, it does not have a built-in feature to automatically rotate credentials. This would require custom automation, increasing operational overhead. Additionally, the term multi-region secret replication is a feature of Secrets Manager, not Parameter Store. Option C is incorrect. Using an Amazon S3 bucket, an event bridge rule, and a Lambda function to rotate credentials is a custom manual solution. This approach requires you to write and maintain the Lambda function, as well as manage the entire orchestration, which results in significant operational overhead and is more prone to error. Option D is incorrect. This solution is a highly manual and complex approach. It involves multiple services, KMS, DynamoDB, Lambda, RDS API, to build a custom solution for credential management and rotation. This would be very difficult to set up and maintain and would have the highest operational overhead of all the options. This brings us to option A, which is the correct and recommended solution. AWS Secrets Manager is a purpose-built service for storing, managing, and automatically rotating secrets, including database credentials. It has a native integration with Amazon RDS for MySQL that allows for automatic rotation. It also supports multi-region secret replication, which directly addresses the requirement to manage credentials across multiple AWS regions. This solution is fully managed by AWS, resulting in the least operational overhead. Therefore, the correct solution is A. Store the credentials as secrets in AWS Secrets Manager. Use multi-region secret replication for the required regions. Configure Secrets Manager to rotate the secrets on a schedule. Question 6. A company hosts an application in a private subnet. The company has already integrated the application with Amazon Cognito. The company uses an Amazon Cognito user pool to authenticate users. The company needs to modify the application so the application can securely store user documents in an Amazon S3 bucket. Which combination of steps will securely integrate Amazon S3 with the application? Choose 2. Create an Amazon Cognito identity pool to generate secure Amazon S3 access tokens for users when they successfully log in. B. Use the existing Amazon Cognito user pool to generate Amazon S3 access tokens for users when they successfully log in. C. Create an Amazon S3 VPC endpoint in the same VPC where the company hosts the application. D. Create a NAT gateway in the VPC where the company hosts the application. Assign a policy to the S3 bucket to deny any request that is not initiated from Amazon Cognito. E. Attach a policy to the S3 bucket that allows access only from the user's IP addresses. Okay, this question is about securely connecting an application in a private subnet to an Amazon S3 bucket using Amazon Cognito for authentication. The solution must ensure that the application can securely store user-specific documents. We need to choose two correct steps. With that in mind, let's look at our options. Option A is a correct and necessary step. An Amazon Cognito user pool is for authentication, verifying a user's identity. An Amazon Cognito identity pool is for authorization, granting temporary AWS credentials to authenticated users. To allow the application to securely access AWS services like S3, the application needs temporary credentials. The identity pool is specifically designed to exchange the user's authenticated identity from the user pool for temporary, limited privilege AWS credentials. Option B is incorrect. The user pool's job is authentication. It confirms the user's identity but doesn't, by itself, grant access to other AWS services like S3. You must use an identity pool in conjunction with the user pool to get the necessary access tokens, credentials. Option C is also a correct and necessary step. The application is in a private subnet, which means it doesn't have a public IP address and cannot access the internet directly. To allow it to communicate with S3, which is a public service, without sending traffic over the public internet, you need a VPC endpoint. A VPC endpoint for S3 allows the private subnet to securely and directly access the S3 service. Option D is incorrect. While a NAT gateway would allow the application to connect to S3, it would send the traffic over the public internet, which is less secure and less efficient than using a VPC endpoint. The second part of the statement, deny any request that is not initiated from Amazon Cognito, is not a valid S3 bucket policy condition. S3 policies can't natively check if a request came from a specific service like Cognito. They check IAM principals, IPs, and other request properties. Option E is incorrect. Users' IP addresses can change frequently, especially for mobile users, making this a highly impractical and unscalable solution. It would also fail for users behind a corporate firewall or NAT, and it doesn't solve the core problem of securely authorizing the application itself to store the files. Therefore, the two correct steps are A and C. You need an identity pool to provide temporary credentials and a VPC endpoint to securely connect the private subnet to S3. Question 7. A company has an automobile sales website that stores its listings in a database on Amazon RDS. When an automobile is sold, the listing needs to be removed from the website and the data must be sent to multiple target systems. Which design should a solutions architect recommend? A. Create an AWS Lambda function triggered when the database on Amazon RDS is updated to send the information to an Amazon Simple Queue service, Amazon SQS, queue for the targets to consume. B. Create an AWS Lambda function triggered when the database on Amazon RDS is updated to send the information to an Amazon Simple Queue service, Amazon SQS, FIFO queue for the targets to consume. C. Subscribe to an RDS event notification and send an Amazon Simple Queue service, Amazon SQS, queue fanned out to multiple Amazon Simple Notification Service, Amazon SNS, topics. Use AWS Lambda functions to update the targets. D. Subscribe to an RDS event notification and send an Amazon Simple Notification Service, Amazon SNS, topic fanned out to multiple Amazon Simple Queue service, Amazon SQS, queues. Use AWS Lambda functions to update the targets. Okay, this question is about creating an event-driven architecture to notify multiple downstream systems when a database record is updated. The goal is to ensure the data is reliably delivered to several targets. Let's look at each option. A. Create an AWS Lambda function triggered when the database on Amazon RDS is updated to send the information to an Amazon Simple Queue service, Amazon SQS, queue for the targets to consume. This option is a good starting point but has a key flaw. There's no native feature in RDS to trigger a Lambda function directly on a database update. While you could set up a custom solution using database triggers and a proxy, it adds complexity. Furthermore, an SQS queue is typically consumed by one or more workers, not by multiple target systems in a fan-out pattern. B. Create an AWS Lambda function triggered when the database on Amazon RDS is updated to send the information to an Amazon Simple Queue service, Amazon SQS, FIFO queue for the targets to consume. This has the same initial flaw as option A, no native trigger from RDS to Lambda. Additionally, using an SQS FIFO queue is unnecessary here. The question doesn't state that the order of messages must be strictly preserved, and FIFO queues have lower throughput and higher cost compared to standard SQS queues. C. Subscribe to an RDS event notification and send an Amazon Simple Queue service, Amazon SQS, queue fanned out to multiple Amazon Simple Notification Service, Amazon SNS, topics. This option is architecturally incorrect. The fan-out pattern in AWS messaging services is from one to many. The correct pattern is to publish from one SNS topic to many SQS queues, not the other way around. Therefore, this design is invalid. D. Subscribe to an RDS event notification and send an Amazon Simple Notification Service, Amazon SNS, topic fanned out to multiple Amazon Simple Queue service, Amazon SQS, queues. Use AWS Lambda functions to update the targets. This is the correct design pattern. RDS can be configured to send event notifications, e.g., a database table change, to an SNS topic. SNS is a publish/subscribe service that can then fan out this single message to multiple subscribers. These subscribers would be the different target systems. By using separate SQS queues for each target, you decouple them and ensure each system can process the message at its own pace. The Lambda functions would then poll their respective SQS queues and process the data to update their targets. This is a highly scalable, decoupled, and reliable solution for distributing event data to multiple consumers. Therefore, the correct design is D. Subscribe to an RDS event notification and send an Amazon Simple Notification Service, Amazon SNS, topic fanned out to multiple Amazon Simple Queue service, Amazon SQS, queues. Use AWS Lambda functions to update the targets. Question 8. A company has a small Python application that processes JSON documents and outputs the results to an on-premises SQL database. The application runs thousands of times each day. The company wants to move the application to the AWS cloud. The company needs a highly available solution that maximizes scalability and minimizes operational overhead. Which solution will meet these requirements? A. Place the JSON documents in an Amazon S3 bucket. Run the Python code on multiple Amazon EC2 instances to process the documents. Store the results in an Amazon Aurora DB cluster. B. Place the JSON documents in an Amazon S3 bucket. Create an AWS Lambda function that runs the Python code to process the documents as they arrive in the S3 bucket. Store the results in an Amazon Aurora DB cluster. C. Place the JSON documents in an Amazon Elastic Block Store, Amazon EBS volume. Use the EBS multi-attach feature to attach the volume to multiple Amazon EC2 instances. Run the Python code on the EC2 instances to process the documents. Store the results on an Amazon RDS DB instance. D. Place the JSON documents in an Amazon Simple Queue service, Amazon SQS, queue as messages. Deploy the Python code as a container on an Amazon Elastic Container Service, Amazon ECS, cluster that is configured with the Amazon EC2 launch type. Use the container to process the SQS messages. Store the results on an Amazon RDS DB instance. Okay, this question is about migrating an application to the AWS cloud. The key requirements are to handle a high volume of frequent, short-lived tasks with a focus on high availability, maximum scalability, and minimum operational overhead. Let's look at each option. A. Place the JSON documents in an Amazon S3 bucket. Run the Python code on multiple Amazon EC2 instances to process the documents. Store the results in an Amazon Aurora DB cluster. This option uses EC2 instances, which require you to manage the underlying servers, including patching, security, and scaling. This increases operational overhead and doesn't provide the level of scalability and cost efficiency needed for an application that runs thousands of times a day but might be idle otherwise. C. Place the JSON documents in an Amazon Elastic Block Store, Amazon EBS volume. Use the EBS multi-attach feature to attach the volume to multiple Amazon EC2 instances. Run the Python code on the EC2 instances to process the documents. Store the results on an Amazon RDS DB instance. This option has multiple issues. EBS volumes are not ideal for storing many small, individual files like JSON documents. The multi-attach feature is primarily for block-level storage on a single volume and is not a suitable data sharing mechanism for this use case. This solution also uses EC2, which, as mentioned, increases operational overhead. D. Place the JSON documents in an Amazon Simple Queue service, Amazon SQS, queue as messages. Deploy the Python code as a container on an Amazon Elastic Container Service, Amazon ECS, cluster that is configured with the Amazon EC2 launch type. Use the container to process the SQS messages. Store the results on an Amazon RDS DB instance. While this is a decoupled, scalable solution, it still involves managing EC2 instances in the background. The ECS launch type of Fargate would be a better choice for minimizing operational overhead, as it is serverless. This solution doesn't fully minimize operational overhead. This brings us to option B, which is the correct and most suitable solution. Perfectly meets all the requirements. Placing the JSON documents in an Amazon S3 bucket is the standard practice for cloud object storage. The key to this solution is using AWS Lambda. AWS Lambda is a serverless compute service that can be automatically triggered when a new object is created in an S3 bucket. It runs the code without requiring you to provision or manage any servers. This provides maximum scalability and high availability, as Lambda automatically scales to handle the thousands of daily requests. Storing the results in an Amazon Aurora DB cluster provides a highly available, scalable, and fully managed database solution. This combination of S3, Lambda, and Aurora offers the least operational overhead, while meeting all performance and availability requirements. Therefore, the correct solution is B. Place the JSON documents in an Amazon S3 bucket. Create an AWS Lambda function that runs the Python code to process the documents as they arrive in the S3 bucket. Store the results in an Amazon Aurora DB cluster. Question 9. A company has an AWS Glue extract, transform, and load ETL job that runs every day at the same time. The job processes XML data that is in an Amazon S3 bucket. New data is added to the S3 bucket every day. A solutions architect notices that AWS Glue is processing all the data during each run. What should the solutions architect do to prevent AWS Glue from reprocessing old data? A. Edit the job to use job bookmarks. B. Edit the job to delete data after the data is processed. C. Edit the job by setting the number of workers field to 1. D. Use a find-matches machine learning ML transform. Okay, this question is about optimizing an AWS Glue ETL job to process only new data and avoid reprocessing old data. This is a common requirement for incremental data loading. The key is to find the right feature that tracks state and processes only what's new. Let's look at each option. A. Edit the job to use job bookmarks. This is the correct solution. AWS Glue job bookmarks track the state of previously processed data during a job run. When the job runs again, AWS Glue uses the bookmark to determine which data has already been processed and only processes the new data. This is the exact feature designed for this incremental loading use case, and it directly solves the problem of reprocessing old data. B. Edit the job to delete data after the data is processed. This option is a terrible idea. Deleting the source data after processing it is a destructive action that would prevent any future audits, historical analysis, or reprocessing if an error occurs. This is not a standard or safe practice for an ETL job. C. Edit the job by setting the number of workers field to 1. This would not prevent the job from reprocessing old data. The number of workers parameter controls the job's parallelization and performance. Setting it to 1 would make the job slower and more expensive, and it would still process all the data in the S3 bucket during each run. D. Use a find-matches machine learning ML transform. A find-matches ML transform is used for data deduplication or finding matching records in a dataset, which is a completely different use case from this problem. It has no functionality to track state for incremental processing. Therefore, the correct solution is A. Edit the job to use job bookmarks. Question 10. A company has created an image analysis application in which users can upload photos and add photo frames to their images. The users upload images and metadata to indicate which photo frames they want to add to their images. The application uses a single Amazon EC2 instance and Amazon DynamoDB to store the metadata. The application is becoming more popular, and the number of users is increasing. The company expects the number of concurrent users to vary significantly depending on the time of day and day of week. The company must ensure that the application can scale to meet the needs of the growing user base. Which solution meets these requirements? A. Use AWS Lambda to process the photos. Store the photos and metadata in DynamoDB. B. Use Amazon Kinesis Data Firehose to process the photos and to store the photos and metadata. C. Use AWS Lambda to process the photos. Store the photos in Amazon S3. Retain DynamoDB to store the metadata. D. Increase the number of EC2 instances to 3. Use provisioned IOPS SSD, IO2, Amazon Elastic Block Store, Amazon EBS, volumes to store the photos and metadata. Okay, this question is about improving the scalability of an image processing application that has variable traffic. The existing architecture is using a single EC2 instance, which is a bottleneck for scalability. The key is to find a highly scalable, serverless, and cost-effective solution. Let's look at each option. A. Use AWS Lambda to process the photos. Store the photos and metadata in DynamoDB. This option correctly identifies AWS Lambda as a scalable solution for processing. However, storing photos directly in DynamoDB is incorrect. DynamoDB is a NoSQL key value and document database designed for small, predictable data sizes, up to 400 kilobytes per item. It is not suitable for storing large binary objects like images, which would be both expensive and inefficient. B. Use Amazon Kinesis Data Firehose to process the photos and to store the photos and metadata. Kinesis Data Firehose is designed for real-time data streaming and delivery, typically for logs and metrics. It is not an appropriate service for processing images, and it is not a suitable primary storage solution for photos and metadata. Using it for this purpose would be an architectural mismatch. D. Increase the number of EC2 instances to 3. Use provisioned IOPS SSD, IO2, Amazon Elastic Block Store, Amazon EBS, volumes to store the photos and metadata. While increasing the number of EC2 instances provides some scalability, it still requires manual management. It doesn't provide the level of serverless scalability needed for traffic that varies significantly. Storing photos on EBS volumes would also be difficult to scale across multiple instances without a shared file system, which adds complexity and operational overhead. This brings us to option C, which is the correct and most suitable solution. It leverages the strengths of multiple AWS services for a robust and scalable architecture. AWS Lambda is a serverless compute service that can automatically scale to handle the variable number of concurrent users. It is an excellent choice for event-driven tasks like processing an uploaded image. Amazon S3 is the ideal service for storing photos. It's an object storage service designed for massive scalability, high durability, and low cost. Keeping the metadata in Amazon DynamoDB is also a great choice, as it is a highly scalable NoSQL database well-suited for the small, structured data of metadata. Therefore, the correct solution is C. Use AWS Lambda to process the photos. Store the photos in Amazon S3. Retain DynamoDB to store the metadata. Question 11. A solutions architect must design a solution that uses Amazon CloudFront with an Amazon S3 origin to store a static website. The company's security policy requires that all website traffic be inspected by AWS WAF. How should the solutions architect comply with these requirements? A. Configure an S3 bucket policy to accept requests coming from the AWS WAF Amazon Resource Name, ARN, only. B. Configure Amazon CloudFront to forward all incoming requests to AWS WAF before requesting content from the S3 origin. C. Configure a security group that allows Amazon CloudFront IP addresses to access Amazon S3 only. Associate AWS WAF to CloudFront. D. Configure Amazon CloudFront and Amazon S3 to use an Origin Access Identity (OAI) to restrict access to the S3 bucket. Enable AWS WAF on the distribution. Okay, this question is about securely configuring a static website hosted on Amazon S3 and delivered via Amazon CloudFront, while also meeting the requirement to inspect all traffic with AWS WAF. The solution must ensure that S3 is only accessible through CloudFront, and that CloudFront itself is protected by WAF. Let's look at each option. A. Configure an S3 bucket policy to accept requests coming from the AWS WAF Amazon Resource Name, ARN, only. This option is incorrect. AWS WAF is a web application firewall that inspects requests before they reach CloudFront. It does not have an ARN that can be used in an S3 bucket policy to grant access. S3 bucket policies can be configured to grant access to a CloudFront Origin Access Identity, OAI, not WAF. B. Configure Amazon CloudFront to forward all incoming requests to AWS WAF before requesting content from the S3 origin. This option is architecturally incorrect. AWS WAF is a service you associate with a CloudFront distribution, not a destination that CloudFront forwards requests to. The flow is user-CloudFront-WAF at the edge CloudFront-S3. WAF inspects the request at the edge before it gets forwarded to the origin. C. Configure a security group that allows Amazon CloudFront IP addresses to access Amazon S3 only. Associate AWS WAF to CloudFront. This option is also incorrect. Amazon S3 is not a VPC service, so you cannot apply a security group to it. S3 is a public service that you control access to using bucket policies, not network security controls like security groups. This brings us to option D, which is the correct and most secure solution. An Origin Access Identity, OAI, is a special CloudFront user that you associate with your distribution. You then update the S3 bucket policy to only allow access from this OAI. This prevents users from bypassing CloudFront and accessing the S3 bucket directly via its public URL. The second part of the option, enable AWS WAF on the distribution, is the standard way to apply WAF rules to a CloudFront distribution. The WAF rules will inspect all traffic coming to the CloudFront distribution before it is forwarded to the S3 origin. This combination meets both the S3 origin security requirement and the WAF inspection requirement with the least operational overhead. Therefore, the correct solution is D. Configure Amazon CloudFront and Amazon S3 to use an Origin Access Identity, OAI, to restrict access to the S3 bucket. Enable AWS WAF on the distribution. Question 12. A company's image hosting website gives users around the world the ability to upload, view, and download images from their mobile devices. The company currently hosts the static website in an Amazon S3 bucket. Because of the website's growing popularity, the website's performance has decreased. Users have reported latency issues when they upload and download images. The company must improve the performance of the website. Which solution will meet these requirements with the least implementation effort? A. Configure an Amazon CloudFront distribution for the S3 bucket to improve the download performance. Enable S3 transfer acceleration to improve the upload performance. B. Configure Amazon EC2 instances of the right sizes in multiple AWS regions. Migrate the application to the EC2 instances. Use an application load balancer to distribute the website traffic equally among the EC2 instances. Configure AWS Global Accelerator to address global demand with low latency. C. Configure an Amazon CloudFront distribution that uses the S3 bucket as an origin to improve the download performance. Configure the application to use CloudFront to upload images to improve the upload performance. Create S3 buckets in multiple AWS regions. Configure replication rules for the buckets to replicate users' data based on the user's location. Redirect downloads to the S3 bucket that is closest to each user's location. D. Configure AWS Global Accelerator for the S3 bucket to improve network performance. Create an endpoint for the application to use Global Accelerator instead of the S3 bucket. Okay, this question is about improving the global performance of a static website hosted on S3, specifically addressing both download and upload latency. The key is to find a solution that requires the least implementation effort. Let's look at each option. A. Configure an Amazon CloudFront distribution for the S3 bucket to improve the download performance. Enable S3 transfer acceleration to improve the upload performance. This is the correct solution. CloudFront is a content delivery network, CDN, that caches content at edge locations around the world, significantly reducing latency for downloads. S3 transfer acceleration uses CloudFront's globally distributed edge locations to optimize the path for data uploads. It's a simple two-step process to enable these features on an existing S3 bucket. This approach is highly effective and requires minimal effort, as both are features that can be enabled with just a few clicks. B. Configure Amazon EC2 instances of the right sizes in multiple AWS regions. Migrate the application to the EC2 instances. Use an application load balancer to distribute the website traffic equally among the EC2 instances. Configure AWS Global Accelerator to address global demand with low latency. This is an overly complex solution. It involves a full re-architecture and migration from a simple static website hosted on S3 to a multi-region, server-based application, which would require significant implementation effort. C. Configure an Amazon CloudFront distribution that uses the S3 bucket as an origin to improve the download performance. Configure the application to use CloudFront to upload images to improve the upload performance. Create S3 buckets in multiple AWS regions. Configure replication rules for the buckets to replicate users' data based on the user's location. Redirect downloads to the S3 bucket that is closest to each user's location. This option is also highly complex. While it correctly identifies CloudFront for downloads, it proposes a multi-region S3 setup with replication rules and custom redirection logic. S3 transfer acceleration already provides a built-in, low-effort solution for global uploads without needing to manage multi-region buckets and redirection rules manually. D. Configure AWS Global Accelerator for the S3 bucket to improve network performance. Create an endpoint for the application to use Global Accelerator instead of the S3 bucket. This option is incorrect. AWS Global Accelerator improves the performance of TCP and UDP protocols and is best suited for applications running on EC2 or other VPC-based services. It is not designed to directly accelerate static content delivery from S3. While you can use it with S3 via a network load balancer, it's not the native, low-effort solution that CloudFront and S3 transfer acceleration provide for this use case. Therefore, the correct solution is A. Configure an Amazon CloudFront distribution for the S3 bucket to improve the download performance. Enable S3 transfer acceleration to improve the upload performance. Question 13. A global company is using Amazon API Gateway to design REST APIs for its Loyalty Club users in the US East 1 region and the AP Southeast 2 region. A solutions architect must design a solution to protect these API Gateway managed REST APIs across multiple accounts from SQL injection and cross-site scripting attacks. Which solution will meet these requirements with the least amount of administrative effort? A. Set up AWS WAF in both regions. Associate regional web ACLs with an API stage. B. Set up AWS Firewall Manager in both regions. Centrally configure AWS WAF rules. C. Set up AWS Shield in Bath regions. Associate regional web ACLs with an API stage. D. Set up AWS Shield in one of the regions. Associate regional web ACLs with an API stage. Okay, this question is about protecting APIs against common web exploits like SQL injection and cross-site scripting, XSS, in a multi-region, multi-account environment. The key is to find the solution that provides centralized management with the least administrative effort. Let's look at each option. A. Set up AWS WAF in both regions. Associate regional web ACLs with an API stage. This is a possible solution, as AWS WAF is the correct service for protecting against SQL injection and XSS. However, it requires a separate configuration for each AWS account and each region. In a multi-account, multi-region setup, this would be a manual and time-consuming process with a high amount of administrative overhead. B. Set up AWS Firewall Manager in both regions. Centrally configure AWS WAF rules. This is the correct solution. AWS Firewall Manager is a security management service that allows you to centrally configure and manage firewall rules across multiple AWS accounts and resources from a single place. It integrates with AWS WAF, allowing a security administrator to define a single set of WAF rules and have them automatically deployed and enforced across all specified accounts and regions. This dramatically reduces administrative effort, as you don't have to manually configure WAF for each account and region individually. C. Set up AWS Shield in both regions. Associate regional web ACLs with an API stage. This option is incorrect. AWS Shield is a managed distributed denial of service, DDoS protection service. While AWS Shield Advanced includes WAF integration, its primary purpose is to mitigate DDoS attacks, not protect against application-level exploits like SQL injection and XSS. D. Set up AWS Shield in one of the regions. Associate regional web ACLs with an API stage. This option is incorrect for two reasons. First, as mentioned in option C, AWS Shield is for DDoS protection, not application-level exploits. Second, AWS API Gateway APIs are regional. To protect APIs in both US East 1 and AP Southeast 2, you would need security measures in both regions, not just one. Therefore, the correct solution is B. Set up AWS Firewall Manager in both regions. Centrally configure AWS WAF rules. Question 14. A solutions architect is optimizing a website for an upcoming musical event. Videos of the performances will be streamed in real time and then will be available on demand. The event is expected to attract a global online audience. Which service will improve the performance of both the real-time and on-demand streaming? Amazon CloudFront. B. AWS Global Accelerator. C. Amazon Route 53. D. Amazon S3 Transfer Acceleration. Okay, this question is about improving the delivery of video content to a global audience for both live and on-demand streaming. The key is to find a service that is purpose-built to handle both types of content delivery with low latency. Let's look at each option. Amazon CloudFront. This is the correct service. Amazon CloudFront is a global content delivery network, CDN, that is designed to accelerate the delivery of web content, including video. It improves on-demand streaming by caching video files at edge locations around the world, so users can download content from the location closest to them. It also supports live video streaming by providing low-latency delivery of the live stream to a global audience. This service is the perfect fit for both parts of the question. B. AWS Global Accelerator. This is a networking service that improves the availability and performance of applications. It uses the AWS Global Network to route traffic to the optimal endpoint, which can reduce latency. However, it's primarily designed for accelerating TCP and UDP traffic to application endpoints, like EC2 instances or load balancers, and is not a content delivery network. It doesn't cache content, which is a key part of improving performance for on-demand streaming. C. Amazon Route 53. This is a domain name system, DNS, Web service. It translates human-readable domain names into IP addresses and can route users to the nearest AWS region. While it is a crucial component of a global architecture, it does not directly improve the performance of video streaming itself. Its job is to direct traffic, not to deliver content. D. Amazon S3 Transfer Acceleration. This is a feature of Amazon S3 that speeds up the transfer of files as they are uploaded to an S3 bucket over long distances. It's an excellent tool for improving upload performance, but it does nothing to help with the download or real-time streaming of content to the end users. It only addresses half of the problem. Therefore, the correct solution is A. Amazon CloudFront. Question 15. A solutions architect needs to help a company optimize the cost of running an application on AWS. The application will use Amazon EC2 instances, AWS Fargate, and AWS Lambda for compute within the architecture. The EC2 instances will run the data ingestion layer of the application. EC2 usage will be sporadic and unpredictable. Workloads that run on EC2 instances can be interrupted at any time. The application front-end will run on Fargate, and Lambda will serve the API layer. The front-end utilization and API layer utilization will be predictable over the course of the next year. Which combination of purchasing options will provide the most cost-effective solution for hosting this application? Choose 2. A. Use spot instances for the data ingestion layer. B. Use on-demand instances for the data ingestion layer. C. Purchase a 1-year compute savings plan for the front-end and API layer. D. Purchase 1-year all-upfront reserved instances for the data ingestion layer. E. Purchase a 1-year EC2 instance savings plan for the front-end and API layer. Okay, this question is about choosing the most cost-effective EC2 purchasing options for different parts of an application based on their workload characteristics. We have 2 distinct use cases: an unpredictable, interruptible workload and a predictable, stable workload. Let's look at each option. A. Use spot instances for the data ingestion layer. This is a correct choice. The question states that the EC2 data ingestion workload is sporadic and unpredictable, and can be interrupted at any time. This description is a perfect match for spot instances. Spot instances use unused EC2 capacity and can provide a significant discount of up to 90% compared to on-demand prices. They are ideal for flexible, stateless, or fault-tolerant workloads that can be interrupted with a 2-minute warning. B. Use on-demand instances for the data ingestion layer. This is incorrect. While on-demand instances provide flexibility and are good for unpredictable workloads, they are the most expensive option. Since the workload can be interrupted, a much cheaper option exists. C. Purchase a 1-year compute savings plan for the front-end and API layer. This is also a correct choice. The question states that the front-end, Fargate, and API layer, Lambda, utilization will be predictable over the course of the next year. A compute savings plan offers a flexible pricing model that provides significant discounts in exchange for a commitment to a consistent amount of usage, measured in $/hour, over a 1-year or 3-year term. The key here is compute savings plan, as it applies automatically to usage across EC2, Fargate, and Lambda, providing the best flexibility for the predictable portion of the workload. D. Purchase 1-year all-upfront reserved instances for the data ingestion layer. This is incorrect. Reserved instances are not a good fit for a workload that is sporadic and unpredictable. They are best for workloads with a consistent, predictable usage pattern. Furthermore, they are primarily for EC2 instances and would not apply to the Fargate or Lambda parts of the application. The cost would also be higher and less flexible than using spot instances for this type of workload. E. Purchase a 1-year EC2 instance savings plan for the front-end and API layer. This is incorrect. An EC2 instance savings plan applies only to EC2 instances, not to AWS Fargate or AWS Lambda. The question specifies that both Fargate and Lambda are used for the front-end and API layers, so this plan would not cover all the compute usage and therefore is not the most cost-effective solution. Therefore, the 2 correct solutions are A and C. Using spot instances for the sporadic, interruptible workload, and a compute savings plan for the predictable Fargate and Lambda workloads is the most cost-effective combination. Question 16. A company has a data ingestion workflow that includes the following components: an Amazon Simple Notification Service, Amazon SNS, topic that receives notifications about new data deliveries, an AWS Lambda function that processes and stores the data. The ingestion workflow occasionally fails because of network connectivity issues. When failure occurs, the corresponding data is not ingested unless the company manually reruns the job. What should a solutions architect do to ensure that all notifications are eventually processed? A. Configure the Lambda function for deployment across multiple availability zones. B. Modify the Lambda function's configuration to increase the CPU and memory allocations for the function. C. Configure the SNS topics retry strategy to increase both the number of retries and the wait time between retries. D. Configure an Amazon Simple Queue Service, Amazon SQS, queue as the on-failure destination. Modify the Lambda function to process messages in the queue. Okay, this question is about making an event-driven workflow more resilient to temporary failures. The current setup, SNS triggering a Lambda function, is failing due to network issues, and the messages are being lost. The goal is to ensure that even failed messages are eventually processed without manual intervention. Let's look at each option. A. Configure the Lambda function for deployment across multiple availability zones. This is an incorrect solution. AWS Lambda is a highly available serverless service by design. It already runs across multiple availability zones automatically, so there is no manual configuration step to do this. The problem is a network connectivity issue during the function's execution, not the availability of the function itself. B. Modify the Lambda function's configuration to increase the CPU and memory allocations for the function. This is an incorrect solution. Increasing CPU and memory might help with some performance issues, but it will not solve the underlying problem of intermittent network connectivity failures. A network failure will still cause the function to fail, regardless of its processing power. C. Configure the SNS topics retry strategy to increase both the number of retries and the wait time between retries. This is an incorrect solution. While SNS does have a retry policy for delivering messages to Lambda, this policy is primarily for addressing issues with the destination endpoint itself, not for when a function fails during execution. When a Lambda function is asynchronously invoked by SNS and fails, Lambda has its own retry behavior, defaulting to 2 retries. If all retries fail, the message is lost. Extending the SNS retry policy is not a robust way to handle application-level failures and does not guarantee eventual processing. D. Configure an Amazon Simple Queue Service, Amazon SQS, queue as the on-failure destination. Modify the Lambda function to process messages in the queue. This is the correct solution. For asynchronous invocations, like SNS to Lambda, AWS Lambda has a feature called Destinations. You can configure a destination for failed invocations. By setting a Simple Queue Service, SQS, queue as the on-failure destination, anytime the Lambda function fails after all its retries are exhausted, the event payload is automatically sent to the SQS queue. The messages in the queue can then be processed later, either by a separate worker or by the same function, ensuring the data is not lost and is eventually ingested. This is a standard and highly effective pattern for building resilient, event-driven architectures. Therefore, the correct solution is D. Configure an Amazon Simple Queue Service, Amazon SQS, queue as the on-failure destination. Modify the Lambda function to process messages in the queue. Question 17. A company runs multiple workloads on virtual machines, VMs, in an on-premises data center. The company is expanding rapidly. The on-premises data center is not able to scale fast enough to meet business needs. The company wants to migrate the workloads to AWS. The migration is time-sensitive. The company wants to use a lift-and-shift strategy for non-critical workloads. Which combination of steps will meet these requirements? Choose 3. A. Use the AWS Schema Conversion Tool, AWS SCT, to collect data about the VMs. B. Use AWS Application Migration Service. Install the AWS Replication Agent on the VMs. C. Complete the initial replication of the VMs. Launch test instances to perform acceptance tests on the VMs. D. Stop all operations on the VMs. Launch a cutover instance. E. Use AWS App2 container, A2C, to collect data about the VMs. F. Use AWS Database Migration Service, AWS DMS, to migrate the VMs. Okay, this question is about a lift and shift migration of on-premises virtual machines to AWS. The key is to identify the core steps and the correct service for this specific migration strategy, which is also known as rehosting. Let's look at each option. A. Use the AWS Schema Conversion Tool, AWS SCT, to collect data about the VMs. This is not a correct step. AWS SCT is a service used for migrating databases, not entire virtual machines. It helps convert database schemas and code between different database engines. B. Use AWS Application Migration Service. Install the AWS Replication Agent on the VMs. This is a correct step. AWS Application Migration Service, AWS MGN, is the primary service for a lift and shift migration. You install an agent on the source VMs, and it automatically replicates the data to an AWS staging area. This is the first and most critical step in the process. C. Complete the initial replication of the VMs. Launch test instances to perform acceptance tests on the VMs. This is a correct step. Before the final migration, it is a crucial best practice to perform a test. This step uses the replicated data to launch a test instance in AWS, allowing you to confirm that the application functions correctly in the new environment without affecting the live on-premises workload. D. Stop all operations on the VMs. Launch a cutover instance. This is a correct step. This is the final and most important phase of the migration. Once the tests are successful, you perform a cutover. This involves stopping the on-premises VM's operations and launching the final production-ready instance in AWS to take over the workload. E. Use AWS App2 container, A2C, to collect data about the VMs. This is not a correct step. AWS App2 container is a tool used for replatforming applications by converting them into containers. This is a different strategy than a simple lift and shift migration. F. Use AWS Database Migration Service, AWS DMS, to migrate the VMs. This is not a correct step. AWS DMS is a service specifically designed for migrating databases and is not used to migrate virtual machines or other types of workloads. The correct combination of steps that will meet these requirements is B, C, and D. You first use AWS Application Migration Service to replicate the VMs, then you perform a test migration to ensure everything works, and finally, you perform the cutover to move the workload to AWS. Question 18. A security team wants to limit access to specific services or actions in all of the team's AWS accounts. All accounts belong to a large organization in AWS organizations. The solution must be scalable and there must be a single point where permissions can be maintained. What should a solutions architect do to accomplish this? A. Create an ACL to provide access to the services or actions. B. Create a security group to allow accounts and attach it to user groups. C. Create cross-account roles in each account to deny access to the services or actions. D. Create a service control policy in the root organizational unit to deny access to the services or actions. Okay, this question is about centrally managing security permissions across a large number of AWS accounts in an AWS organization. The key requirements are scalability and a single point of management. Let's look at each option. A. Create an ACL to provide access to the services or actions. This is an incorrect solution. ACLs, or access control lists, are used for network traffic filtering, such as network ACLs within a VPC or bucket ACLs for S3. They are not used to control access to specific AWS services or API actions for IAM principles. B. Create a security group to allow accounts and attach it to user groups. This is an incorrect solution. Security groups are stateful firewalls that control inbound and outbound traffic for EC2 instances and other resources. They are not used to manage permissions for AWS services across accounts. C. Create cross-account roles in each account to deny access to the services or actions. This is an incorrect solution because it does not meet the scalability requirement. Creating a cross-account role and policy in each account would be a highly manual and unscalable process, especially in a large organization. It also fails the single point of management requirement. This brings us to option D, which is the correct and most suitable solution. Service control policies, SCPs, are a feature of AWS organizations that allow you to centrally manage permissions for all accounts in an organization. By attaching a deny policy to the root organizational unit, OU, you can enforce that policy across all accounts, preventing IAM users and roles in any account from accessing the specified services or actions. This provides a single, scalable point of control. Therefore, the correct solution is D. Create a service control policy in the root organizational unit to deny access to the services or actions. Question 19. A company needs to retain application log files for a critical application for 10 years. The application team regularly accesses logs from the past month for troubleshooting, but logs older than 1 month are rarely accessed. The application generates more than 10 terabytes of logs per month. Which storage option meets these requirements most cost-effectively? Store the logs in Amazon S3. Use AWS Backup to move logs more than 1 month old to S3 Glacier Deep Archive. B. Store the logs in Amazon S3. Use S3 Lifecycle policies to move logs more than 1 month old to S3 Glacier Deep Archive. C. Store the logs in Amazon CloudWatch logs. Use AWS Backup to move logs more than 1 month old to S3 Glacier Deep Archive. D. Store the logs in Amazon CloudWatch logs. Use Amazon S3 Lifecycle policies to move logs more than 1 month old to S3 Glacier Deep Archive. Okay, this question is about a classic data lifecycle management problem. The goal is to store a massive amount of log data for a very long time, but with different access patterns over that period, all while keeping costs as low as possible. We need a solution that handles both the frequently accessed data and the long-term, rarely accessed archive. Let's look at each option. Store the logs in Amazon S3. Use AWS Backup to move logs more than 1 month old to S3 Glacier Deep Archive. This is not the most cost-effective or standard solution. While AWS Backup can be used for S3, it is designed for a broader range of backup and recovery scenarios, not specifically for cost-optimizing an S3 data lifecycle. Using S3 lifecycle policies is the native, simpler, and more cost-effective way to achieve this. C. Store the logs in Amazon CloudWatch logs. Use AWS Backup to move logs more than 1 month old to S3 Glacier Deep Archive. This option has a fundamental flaw. CloudWatch logs is a service for collecting, monitoring, and analyzing logs, but it is typically more expensive for large-scale, long-term storage compared to S3. Also, as in option A, AWS Backup is not the correct tool for this task. D. Store the logs in Amazon CloudWatch logs. Use Amazon S3 lifecycle policies to move logs more than 1 month old to S3 Glacier Deep Archive. This option is architecturally incorrect. You cannot directly apply an S3 lifecycle policy to data that is stored in CloudWatch logs. While you can export data from CloudWatch logs to S3, this would be a separate, complex process and still suffers from the higher cost of CloudWatch logs for initial storage. This brings us to option B, which is the correct and most cost-effective solution. Storing the logs in Amazon S3 is the ideal starting point. S3 is a highly scalable and durable object storage service perfect for storing raw log files. To meet the requirements, you would start by storing the logs in S3 Standard, which is perfect for the first month when the data is frequently accessed. Then, you would use S3 lifecycle policies to automatically and non-destructively move the objects that are older than 1 month to S3 Glacier Deep Archive. This is a very low-cost storage class designed specifically for long-term data archiving with a retrieval time of up to 12 hours, which perfectly matches the rarely accessed and 10 years requirements. Therefore, the correct solution is B. Store the logs in Amazon S3. Use S3 Lifecycle policies to move logs more than 1 month old to S3 Glacier Deep Archive. Question 20. A medical records company is hosting an application on Amazon EC2 instances. The application processes customer data files that are stored on Amazon S3. The EC2 instances are hosted in public subnets. The EC2 instances access Amazon S3 over the internet, but they do not require any other network access. A new requirement mandates that the network traffic for file transfers take a private route and not be sent over the internet. Which change to the network architecture should a solutions architect recommend to meet this requirement? A. Create a NAT gateway. Configure the route table for the public subnets to send traffic to Amazon S3 through the NAT gateway. B. Configure the security group for the EC2 instances to restrict outbound traffic so that only traffic to the S3 prefix list is permitted. C. Move the EC2 instances to private subnets. Create a VPC endpoint for Amazon S3 and link the endpoint to the route table for the private subnets. D. Remove the Internet gateway from the VPC. Set up an AWS Direct Connect connection and route traffic to Amazon S3 over the Direct Connect connection. Okay, this question is about changing a network architecture to ensure traffic between EC2 instances and Amazon S3 stays within the AWS network, rather than traversing the public internet. The current setup is insecure because the EC2 instances in a public subnet are using an internet gateway to access S3. Let's look at each option. A. Create a NAT gateway. Configure the route table for the public subnets to send traffic to Amazon S3 through the NAT gateway. This is incorrect. A NAT gateway is used to allow instances in a private subnet to access the internet. The EC2 instances are already in a public subnet with an internet gateway, so a NAT gateway would be redundant and would not change the fact that traffic is still routed over the public internet to reach S3. B. Configure the security group for the EC2 instances to restrict outbound traffic so that only traffic to the S3 prefix list is permitted. This is an incorrect solution. A security group is a virtual firewall that controls inbound and outbound traffic at the instance level. While you can use a security group to restrict traffic to S3, this does not change the network path. The traffic would still be routed to S3 over the internet. The goal is to route traffic privately, not just to restrict it. D. Remove the Internet gateway from the VPC. Set up an AWS Direct Connect connection and route traffic to Amazon S3 over the Direct Connect connection. This is an overly complex and incorrect solution. AWS Direct Connect is used to establish a private network connection from your on-premises data center to AWS. It has nothing to do with routing traffic between services within the AWS cloud itself. Additionally, removing the Internet gateway would completely cut off the EC2 instances from any external access they might need. This brings us to option C, which is the correct solution. The best practice for this scenario is to use a VPC endpoint for S3. A VPC endpoint allows you to connect your VPC to an AWS service without requiring an Internet gateway, a NAT device, a VPN connection, or AWS Direct Connect. By moving the EC2 instances to a private subnet and creating a VPC endpoint for S3, you ensure that all traffic between the instances and S3 stays within the AWS private network, which meets the new security requirement. You would then need to update the private subnet's route table to direct traffic to the S3 service through the new VPC endpoint. Therefore, the correct solution is C. Move the EC2 instances to private subnets. Create a VPC endpoint for Amazon S3 and link the endpoint to the route table for the private subnets. Question 21. A company is concerned about the security of its public web application due to recent web attacks. The application uses an application load balancer, ALB. A solutions architect must reduce the risk of DDoS attacks against the application. What should the solutions architect do to meet this requirement? A. Add an Amazon Inspector agent to the ALB. B. Configure Amazon Macie to prevent attacks. C. Enable AWS Shield Advanced to prevent attacks. D. Configure Amazon Guard Duty to monitor the ALB. Okay, This question is about protecting a public web application running behind an application load balancer from DDoS attacks. The key is to identify the AWS service that is specifically designed for DDoS protection at a high level. Let's look at each option. A. Add an Amazon Inspector agent to the ALB. This is an incorrect solution. Amazon Inspector is a service for automated vulnerability management. It scans Amazon EC2 instances, container images, and Lambda functions for software vulnerabilities and unintended network exposure. It requires an agent to be installed on EC2 instances, but it is not a tool for DDoS protection and cannot be used with an ALB. B. Configure Amazon Macie to prevent attacks. This is an incorrect solution. Amazon Macie is a data security service that uses machine learning to discover and protect sensitive data in Amazon S3. Its purpose is to identify data security risks, not to mitigate web attacks like DDoS. D. Configure Amazon GuardDuty to monitor the ALB. This is an incorrect solution. Amazon GuardDuty is an intelligent threat detection service that continuously monitors for malicious activity and unauthorized behavior. While it can detect threats, it is a monitoring and alerting service, not a direct prevention service. It does not provide active DDoS attack mitigation. This brings us to option C, which is the correct solution. AWS Shield is a managed DDoS protection service. All AWS customers automatically benefit from AWS Shield standard, which provides basic protection. However, to get enhanced DDoS protection, especially against sophisticated attacks and to protect specific resources like an ALB, you should subscribe to AWS Shield Advanced. Shield Advanced provides always-on detection and automatic inline mitigations, access to the AWS Shield Response Team, SRT, and DDoS cost protection. It is the specific service designed to prevent DDoS attacks at the scale required for a public web application. Therefore, the correct solution is C. Enable AWS Shield Advanced to prevent attacks. Question 22. A company runs its e-commerce application on AWS. Every new order is published as a message in a RabbitMQ queue that runs on an Amazon EC2 instance in a single availability zone. These messages are processed by a different application that runs on a separate EC2 instance. This application stores the details in a PostgreSQL database on another EC2 instance. All the EC2 instances are in the same availability zone. The company needs to redesign its architecture to provide the highest availability with the least operational overhead. What should a solutions architect do to meet these requirements? A. Migrate the queue to a redundant pair active/standby of RabbitMQ instances on Amazon MQ. Create a multi-AZ auto-scaling group for EC2 instances that host the application. Create another multi-AZ auto-scaling group for EC2 instances that host the PostgreSQL database. B. Migrate the queue to a redundant pair active/standby of RabbitMQ instances on Amazon MQ. Create a multi-AZ auto-scaling group for EC2 instances that host the application. Migrate the database to run on a multi-AZ deployment of Amazon RDS for PostgreSQL. C. Create a multi-AZ auto-scaling group for EC2 instances that host the RabbitMQ queue. Create another multi-AZ auto-scaling group for EC2 instances that host the application. Migrate the database to run on a multi-AZ deployment of Amazon RDS for PostgreSQL. D. Create a multi-AZ auto-scaling group for EC2 instances that host the RabbitMQ queue. Create another multi-AZ auto-scaling group for EC2 instances that host the application. Create a third multi-AZ auto-scaling group for EC2 instances that host the PostgreSQL database. Okay. This question is about improving the high availability of an application that is currently running entirely within a single availability zone on self-managed EC2 instances. The goal is to redesign the architecture to be highly available and to do so with the least amount of operational overhead. Let's look at each option. A. Migrate the queue to a redundant pair active/standby of RabbitMQ instances on Amazon MQ. Create a multi-AZ auto-scaling group for EC2 instances that host the application. Create another multi-AZ auto-scaling group for EC2 instances that host the PostgreSQL database. This option correctly moves the message queue and application to managed, highly available solutions. However, it fails on the database part. Running a PostgreSQL database on an EC2 instance in a multi-AZ auto-scaling group would be extremely difficult to manage. You would have to manually handle replication, failover, backups, and patching, which would result in high operational overhead and is not the recommended approach for high-availability databases. C. Create a multi-AZ auto-scaling group for EC2 instances that host the RabbitMQ. Create another multi-AZ auto-scaling group for EC2 instances that host the application. Migrate the database to run on a multi-AZ deployment of Amazon RDS for PostgreSQL. This option is incorrect because it continues to use a self-managed RabbitMQ on EC2 instances. While an auto-scaling group provides some availability, managing RabbitMQ clusters for high availability across multiple zones is complex and has high operational overhead. A managed service for the message queue is a better choice. D. Create a multi-AZ auto-scaling group for EC2 instances that host the RabbitMQ. Create another multi-AZ auto-scaling group for EC2 instances that host the application. Create a third multi-AZ auto-scaling group for EC2 instances that host the PostgreSQL database. This is the worst option in terms of operational overhead. It requires managing all three components, message queue, application, and database, on EC2 instances across multiple availability zones. This would involve complex configurations for clustering, replication, and failover, which is precisely what the question is trying to avoid. This brings us to option B, which is the correct and most suitable solution. It leverages managed AWS services that are purpose-built for high availability with minimal operational overhead. First, you migrate the self-managed RabbitMQ to a managed Amazon MQ broker. Amazon MQ automatically handles the provisioning of a redundant active/standby pair across two availability zones for high availability. Second, you use a multi-AZ auto-scaling group for the application's EC2 instances. This is a standard and effective way to ensure the application layer is highly available and can scale automatically. Finally, you migrate the database to a multi-AZ deployment of Amazon RDS for PostgreSQL. Amazon RDS for PostgreSQL is a fully managed service that provides synchronous replication and automatic failover to a standby instance in another availability zone, all with zero operational overhead on your part. This combination of Amazon MQ, auto-scaling groups, and Amazon RDS meets all the requirements perfectly. Therefore, the correct solution is B. Migrate the queue to a redundant pair active/standby of RabbitMQ instances on Amazon MQ. Create a multi-AZ auto-scaling group for EC2 instances that host the application. Migrate the database to run on a multi-AZ deployment of Amazon RDS for PostgreSQL. Question 23. A company collects data for temperature, humidity, and atmospheric pressure in cities across multiple continents. The average volume of data that the company collects from each site daily is 500 gigabytes. Each site has a high-speed internet connection. The company wants to aggregate the data from all these global sites as quickly as possible in a single Amazon S3 bucket. The solution must minimize operational complexity. Which solution meets these requirements? A. Turn on S3 transfer acceleration on the destination S3 bucket. Use multi-part uploads to directly upload site data to the destination S3 bucket. B. Upload the data from each site to an S3 bucket in the closest region. Use S3 cross-region replication to copy objects to the destination S3 bucket. Then remove the data from the origin S3 bucket. C. Schedule AWS Snowball Edge Storage optimized device jobs daily to transfer data from each site to the closest region. Use S3 cross-region replication to copy objects to the destination S3 bucket. D. Upload the data from each site to an Amazon EC2 instance in the closest region. Store the data in an Amazon Elastic Block Store, Amazon EBS volume. At regular intervals, take an EBS snapshot and copy it to the region that contains the destination S3 bucket. Restore the EBS volume in that region. Okay, this question is about a company that needs to quickly and simply transfer large volumes of data from multiple global locations to a single Amazon S3 bucket. The key constraints are speed, low operational complexity, and the fact that all locations have high-speed internet. Let's look at each option. A. Turn on S3 transfer acceleration on the destination S3 bucket. Use multi-part uploads to directly upload site data to the destination S3 bucket. This is the correct solution. S3 transfer acceleration uses CloudFront's globally distributed edge locations to optimize data transfer over the public internet. Data from each site is sent to the nearest edge location, and then it is routed to the destination S3 bucket over Amazon's private, high-speed network. This significantly reduces latency caused by geographical distance and variable internet conditions. Combining this with multi-part uploads, which breaks large files into smaller parts for parallel uploading, ensures the fastest possible transfer with minimal implementation effort. This option perfectly meets the requirements for speed and low operational complexity. B. Upload the data from each site to an S3 bucket in the closest region. Use S3 cross-region replication to copy objects to the destination S3 bucket. Then remove the data from the origin S3 bucket. This option is not ideal. It adds unnecessary complexity and cost. The data would still have to travel over the public internet to the regional S3 bucket, and then cross-region replication would incur data transfer costs and additional latency. It's a more convoluted process than using S3 transfer acceleration. C. Schedule AWS Snowball Edge Storage optimized device jobs daily to transfer data from each site to the closest region. Use S3 cross-region replication to copy objects to the destination S3 bucket. This is an incorrect solution. AWS Snowball Edge devices are designed for offline data transfer in petabyte-scale migrations, or when a high-speed internet connection is unavailable. Using a physical device for a daily 500 gigabytes transfer with a high-speed internet connection is overkill, very expensive, and adds significant operational overhead and time. D. Upload the data from each site to an Amazon EC2 instance in the closest region. Store the data in an Amazon Elastic Block Store, Amazon EBS volume. At regular intervals, take an EBS snapshot and copy it to the region that contains the destination S3 bucket. Restore the EBS volume in that region. This is an overly complex and highly inefficient solution. It requires managing EC2 instances, EBS volumes, and snapshots, which introduces significant operational overhead. The entire process of taking and copying snapshots is not designed for the quick and continuous aggregation of new data. Therefore, the correct solution is A. Turn on S3 transfer acceleration on the destination S3 bucket. Use multi-part uploads to directly upload site data to the destination S3 bucket. Question 24. A company is running a multi-tier web application on premises. The web application is containerized and runs on a number of Linux hosts connected to a PostgreSQL database that contains user records. The operational overhead of maintaining the infrastructure and capacity planning is limiting the company's growth. A solutions architect must improve the application's infrastructure. Which combination of actions should the solutions architect take to accomplish this? Choose 2. Migrate the PostgreSQL database to Amazon Aurora. B. Migrate the web application to be hosted on Amazon EC2 instances. C. Set up an Amazon CloudFront distribution for the web application content. D. Set up Amazon Elasticache between the web application and the PostgreSQL database. E. Migrate the web application to be hosted on AWS Fargate with Amazon Elastic Container Service, Amazon ECS. Okay, this question is about moving a containerized on-premises application to AWS to reduce operational overhead. The current setup involves managing both the container hosts and a PostgreSQL database. The goal is to find a solution that makes both the compute and the database layers simpler to manage and more scalable. Let's look at each option. Migrate the PostgreSQL database to Amazon Aurora. This is a correct action. The company is currently managing its own PostgreSQL database, which involves tasks like patching, backups, and scaling. By migrating to Amazon Aurora, a managed relational database service, the company offloads all of this operational overhead to AWS. Aurora is fully compatible with PostgreSQL and offers higher performance and availability, making it an excellent choice. B. Migrate the web application to be hosted on Amazon EC2 instances. This is an incorrect action. The application is already containerized on Linux hosts. Migrating it to Amazon EC2 would just move the problem. The company would still need to manage the EC2 instances, their operating systems, and capacity planning, which is the exact problem they are trying to solve. C. Set up an Amazon CloudFront distribution for the web application content. This is an incorrect action. CloudFront is a content delivery network, CDN, that improves the performance of content delivery to end users. While this is a good practice for web applications, it does not address the core issue of managing the underlying compute and database infrastructure. It does not reduce the operational overhead. D. Set up Amazon Elasticache between the web application and the PostgreSQL database. This is an incorrect action. Amazon Elasticache is a caching service that can significantly improve application performance and reduce database load. However, like CloudFront, it is an optimization. It does not fundamentally change the operational overhead associated with managing the application's core compute and database services. E. Migrate the web application to be hosted on AWS Fargate with Amazon Elastic Container Service, Amazon ECS. This is a correct action. The application is already containerized, so a serverless container service is a perfect fit. AWS Fargate is a compute engine for Amazon ECS that lets you run containers without managing the underlying servers or clusters. This directly addresses the problem of maintaining the infrastructure and capacity planning, dramatically reducing the operational overhead for the web application. Therefore, the correct combination of actions is A and E. Moving the database to a managed service like Amazon Aurora, and the containerized application to a serverless container platform like AWS Fargate with Amazon ECS will significantly reduce operational overhead and improve scalability. Question 25. A company is preparing to store confidential data in Amazon S3. For compliance reasons, the data must be encrypted at rest. Encryption key usage must be logged for auditing purposes. Keys must be rotated every year. Which solution meets these requirements and is the most operationally efficient? Server-side encryption with customer-provided keys, SSEC. B. Server-side encryption with Amazon S3 managed keys, SSE-S3. C. Server-side encryption with AWS KMS keys, SSE-KMS, with manual rotation. D. Server-side encryption with AWS KMS keys, SSE-KMS, with automatic rotation. Okay, this question is about choosing the right S3 encryption option for a very specific set of requirements. At-rest encryption, key usage logging for auditing, and key rotation. The solution must also be the most operationally efficient. Let's look at each option. Server-side encryption with customer-provided keys, SSEC. This option places the responsibility of key management, including rotation and logging, entirely on the customer. S3 does not store the key, and it must be provided with every request. This would be a high-effort solution and is not operationally efficient. It also doesn't provide automatic logging for auditing purposes within AWS. B. Server-side encryption with Amazon S3 managed keys, SSE-S3. This option is very simple and operationally efficient. However, it does not meet all the requirements. With SSE-S3, AWS manages the keys and their rotation. Key usage is not logged to a service like CloudTrail for customer auditing, as the key is managed entirely by S3. This fails the auditing requirement. C. Server-side encryption with AWS KMS keys, SSE-KMS, with manual rotation. This option addresses the key logging requirement. AWS KMS automatically logs all key usage to CloudTrail for auditing purposes. However, it fails the operational efficiency requirement by specifying manual rotation. Manual key rotation requires you to create new keys and re-encrypt data, which is a significant administrative burden and is not the most efficient way to handle yearly rotation. This brings us to option D, which is the correct and most suitable solution. SSE-KMS addresses all the requirements. The data is encrypted at rest using keys managed by KMS. All API calls to KMS for encryption and decryption are automatically logged to AWS CloudTrail, satisfying the auditing requirement. The most crucial part of this option is with automatic rotation. AWS KMS can be configured to automatically rotate customer-managed keys every year, which directly meets the key rotation requirement with the least operational overhead. Therefore, the correct solution is D. Server-side encryption with AWS KMS keys, SSE-KMS, with automatic rotation. Thanks for watching. If you found this video interesting and helpful, please like, share, and subscribe to our channel. See you in the next video. Happy learning!